So now we are going to move towards the concept of convolution. Right, so in the concept of convolution, before going to the concept of convolution, let us see how the concept starts. Right, so initially I will be considering the discrete time unit impulse, a discrete time unit impulse for which the response we are going to get is nothing but discrete time impulse response. So here we are giving an impulse as an input, and the response of the system is going to be the impulse response, correct? Now, if I give an input which is a delayed unit impulse, if I give an input which is a delayed unit impulse, then what is the result we are going to get? If I give the input as a delayed unit impulse, the response that is expected is very good. So delayed impulse response, isn't it? It is a delayed impulse response. Now, how are we confident that if I give del of n minus 1, the response is h of n minus 1? What is the reason for this confidence? That if you delay the input, the output will also be equally delayed. Very good. Because of the fact that this system is a time invariant system. Because it is a time invariant system. That is the reason why this is happening. And similarly, if I give the input as del of n minus 2, the response of the system is h of n minus 2. Del of n minus 3, h of n minus 3. And similarly, del of n plus 1, here it is h of n plus 1. Del of n plus 2, here it is h of n plus 2. All because of the concept of time invariance. All because of the concept of time invariance. If I multiply, let us say A, can I have the same A here? If I multiply A over here, can I have the same A over here? Why? Very good, because of the linear property. So it is nothing but the scaling property or a homogeneity property which says that if I keep A here, here also there will be A. And because our system is linear, this should happen. And because of the additivity property in the linearity, so if I add all the inputs, even the outputs will also be added together. All the outputs are going to be added together. Now, what I'll do here is that I will be multiplying with x of 0. I'll be multiplying with x of 0, which is again a scalar quantity. This will be a sample value, right? A scalar value. So x of 0 if I give here, here also I will be having x of 0. Let me write x of 0. If I keep x of 1 here, here I will be having x of 1. If I give x of 2, here also I will be having x of 2, x of 3, x of 3 over here, x of minus 1, x of minus 1 here, x of minus 2, here x of minus 2. Correct? So if I'm adding all of them over here, this is something like x of k into del of n minus k. X of k into del of n minus k, and the summation is going to be from minus 2 to the value of 3. The summation will be from k is equal to minus 2 to the value of k is equal to 3. So k is equal to minus 2 to 3, x of k del of n minus k. X of k del of n minus k. And the response of the system is summation k is equal to minus 2 to 3, x of k, h of n minus k. Please let me know whether you have understood this or not. If I add all of them, I'm going to get something like this. If I add all of these, I'm going to get something like this. Please let me know whether this is clear or not. So in a generalized case, this is nothing but a specific case. I'm considering only from -2 to the value of 3. But in a generalized case, I can take it from minus infinity to the value of plus infinity. Can I? In a generalized case, can I take it from minus infinity to the value of infinity? Then what do we call this particular signal as? Can I call this signal as x of n? Because we have seen that just before this concept, we have seen that any generalized signal f of n can be represented as summation k is equal to minus infinity to infinity f of k del of n minus k. Now if I am having something called as summation minus infinity to infinity x of k del of n minus k, can't I write it as x of n? Can't I write it as x of n? Absolutely yes, we can write like this. In the same way, this part can also be extended from minus infinity to the value of infinity. So summation k is equal to minus infinity to the value of infinity x of k h of n minus k. X of k h of n minus k. Summation k is equal to minus infinity to infinity x of k h of n minus k. So this, if you are giving the input as x of n passing through an LDA system, the response is what we call as y of n. The response is what we call as y of n. Okay. So therefore, the response of LDA system, for input x of n and impulse response h of n is given by y of n is equal to summation x of k into h of n minus k. X of k into h of n minus k, where the value of k is changing from minus infinity to infinity. Where the value of k is changing from minus infinity to infinity. This can also be called as x of n convolved with it of h of n. This can also be called as y of n is equal to x of n convolved with it of h of n. Okay, so this operator that we have over here is what we call as a convolution operator. We call it as a convolution operator. Please take it down till here and just let me know once this is completed. Okay. So impulse response is that, for example, if I have to make you understand in a very simple words, I'm sure that all of you know about simple pendulum, right? All of you know about simple pendulum, right? So either a simple pendulum or you can consider, right? Let us take an example of simple pendulum. Okay. See, so when I push the simple pendulum just by giving some excitation like this. So when I give an excitation like this, what happens? The simple pendulum will get excited and slowly it reaches to 0. Correct? So if I give more input, more excitation, it will go like this and slowly it comes back to 0. It means that when I give an excitation at some instant, then that excitation can be carried forward to more amount of time and later it is going to come back to rest. So if I consider the disturbance that I am giving at a single instant as an impulse, if whatever disturbance that I am giving to a simple pendulum as an impulse, then the response of that particular simple pendulum is what we are calling as an impulse response. Now, if I want to calculate the output of the system, so what should I do? I have to see all the inputs that I have given at different instances and what is the output that I got. For example, if I give an impulse as an input, what does it mean? If I have given the impulse at n equal to 0 as an input, if the response is something like this, let us say the response that I got is something like 1 to 1. Okay, so if I give the input at n equal to 0, what I am getting? I am getting an output which is nothing but the impulse response, whose values of the signal is nothing but at n equal to 0 it is 1, at n equal to 1 it is 2, and at n equal to 2 it is 1. Is this clear? That if I give an impulse at an instant of n equal to 0, the response that I am getting is what we are calling as an impulse response, which is 1, 2, 1. 1, 2, 1. Now if I give the input at the instant of n equal to 1, if I give the input at the instant of n equal to 1, then what is the output which is expected? If I give an input at n equal to 1, from the concept of time invariance, if this is h of n, this obviously should be, this is h of n, isn't it? So obviously this should be del of h of n minus 1. This should be h of n minus 1. Considering that del of n, and this is h of n, del of n minus 1, this should be h of n minus 1. Right? So how the h of n minus 1 is going to be? 0, 1, 2, 1. Okay, so this is what we call as the impulse response, which is delayed. So now when I am applying the input, let us say that if I am adding these two, then if my input is this one, then what is the output? The output is nothing but the summation of them, which is going to be 1, 3, 3, 1. I'm just adding 1 and 1 here. Here it is 1, here it is 3, here it is 3, and here it is 1. So if I'm applying the input at, if I'm applying the input called as 1, 1, then the output passing through the system is going to be 1, 3, 3, 1. See, please understand, h of n minus 1 means either moving the signal towards right or the arrow towards left. The arrow towards left. So when you move the arrow towards left, it is going to be something like this. See, this is what we call as a output of the system. This is what we call as a output of the system. This is what we call as an impulse response. That because we know this is nothing but a unit impulse that we have applied. This is nothing but unit impulse, right? It means that if you are applying an impulse at the instant of n equal to 0, this is what we call as a unit impulse. And the response of the system that we got is something like this. This is what we call as a impulse response. Now, what I'm doing here is that I have considered two unit impulses. I have just added them. Then I got my input called as 1, 1. This is what I'm going to call as input. So input here is nothing but two impulses, one at n equal to 0 and the other at n equal to 1. So what is the output I got? The output is nothing but something called as 1, 3, 3, 1. So in a way, if you see what we have applied on the input, we know the input is nothing but 1, 1. This is nothing but the input. The impulse response is nothing but 1, 2, 1. The response that we got is nothing but 1, 3, 3, 1. The response we got is nothing but 1, 3, 3, 1. This is what we call as our output. Now the relation between these all three expressions, that x of n, h of n and y of n can be given by y of n is going to be equal to x of n convolved with the of h of n. So to get this operator, to get this output of y of n, what am I applying between x of n and h of n? It is simply the convolution. It is simply the convolution. Okay. So in a very simple words, what we are doing here, for an impulse we are seeing the response, for the delayed input we are seeing the delayed impulse response. So then we are adding them together. This is the total input that I got, and I am seeing what is the total output. This is nothing but the total output. So the difference between response and the output. Response and output both are same. But when I told about response here, I told it's an impulse response. This is also a response, this is also a response, this is also a response. All of them are responses. But specifically this is what we called as impulse response. Why? Because here the input is nothing but impulse. Here the output, this is also a delayed input response, because here I have applied a delayed input. So when I add them together to show that what are the inputs that I have applied, I have applied 1, 1. What is the meaning of 1, 1? Two impulses, one at n equal to 0, the other at n equal to 1. So combined, what is the output? We are adding them because here we have added them together. So that here also it is added, a simple linear property. So we have added them and we are calculating what is the total output. Okay. When you apply the input called as 1, 1 and your system is having an impulse response of 1, 2, 1, the response of the system is nothing but 1, 3, 3, 1. 1, 3, 3, 1. Till here, is it clear to you, or if you have any doubts, please clear it off. It's a very, very important concept. See, h of n is nothing but the impulse response. H of n is nothing but the impulse response. Did we understand what is an impulse response? So, impulse response is simply when you apply input. When you apply input as an impulse, the response that we get from a system is what we call as an impulse response. Right? If I apply the input as an impulse, this is nothing but the impulse, isn't it? Then the response that we got is nothing but the impulse response. So there is a question that how can we differentiate between H11? This is not clear. See, here we are having an impulse at n is equal to 0, right? Here nothing is mentioned, it means that this is nothing but 0 here and 0 here. And here we are having 0, 0, 1. This is what we called as del of n. This is what we called as del of n minus 1, correct? And we have learned that when we apply del of n, the output is nothing but h of n. And here I have given, okay, so now the question is that how h of n is 1, 2, 1. This is something that I have assumed. This is something that I have assumed. Okay, so if I give the input del of n, let my output be h of n. And what is h of n? It is something like this. Okay, so now logically, if I delay the input, which is nothing but my impulse response, then my output should also be delayed, right? Yes, if I delay my input, my output should also be delayed, correct? Yes or no? Now what I am doing is that I am just adding both of them. When I add both of them, then the input, total input that I am applying is nothing but 1 at n equal to 0, and at n equal to 1 it is 1, right? So here also I am doing the same thing. I am just adding h of n and h of n minus 1, because if I add here the inputs, the responses should also be added, which is nothing but the linear property. So if I apply the input called as 1, 1, if I apply the input called as 1, 1, then the response is nothing but 1, 3, 3, 1. How I got this 1, 3, 3, 1? 1, 3, 3 and 1. In a way, this relation between input, impulse response and output is what we call as a The relation that we are having between input, impulse response and output is what we call as x of n convolved with h of n is going to be y of n. So we have to apply the operation of convolution to get this particular output. This is something that we have learned separately, correct? So what we have learned convolution as, so y of n is going to be equal to summation x of k h of n minus k, where the value of k is changing from minus infinity to infinity, right? So k is equal to minus infinity to infinity, x of k h of n minus k. So indirectly what we are doing, see, how did we get this particular result? How did we get this result? When I explained over there, you told I have understood this one, that if I apply del of n, I got h of n. If I apply del of n minus 1, I got h of n minus 1, del of n minus 2, h of n minus 2, del of n plus 1, h of n plus 1. Then what we have done? We have added all of them here. Here also we have added. Why it is added? It is because of the additivity. Here also I have done the same thing, isn't it? When I give del of n as an input, the only thing that I have done here is that I have just added numbers to it. The only thing that I have done here is that I have just added numbers to it. Input is del of n, h of n, del of n minus 1, h of n minus 1. If I add them, here also it is added. Isn't this what we have discussed earlier? Okay, so if input del of n is multiplied with 2, then here it will be 2, then here also it will be 2. So 2, 4 and 2. This is nothing but the scaling property. This is nothing but the scaling property, right? So now if I add these two things together, then at n equal to 0 you are having a value of 2. At n is equal to 0 you are having a value of 2. At n equal to 1 you are having a single 1. So what happens to the output here? It becomes 2, it becomes 5, it becomes 4 here, and it becomes 1 here. Isn't this what we have learned? Del of n gives h of n, del of n minus 1 gives h of n minus 1, and so on. You add here, you add here. We call this as input. This is what we call as output. So what we have done here, the result of output that we are getting is nothing but this, which we have written in terms of a formula. I told you the formula, which is nothing but summation k is equal to minus infinity infinity x of k h of n minus k. So if you try to visualize what is convolution, it is nothing but the excitations that you are giving at different instants. N is equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4. And for every disturbance that you are giving, you are noting the response. For the second disturbance, you are again noting the response. For the third disturbance, you are again noting the response. If you add all these inputs, you are adding all the response. The output is what we call as the convoluted response. The output is what we are calling as the convoluted response. So for every instant, whatever input you are giving, every disturbance that you are giving, you are taking the outputs. Okay, here the disturbance is what I am calling as impulse. Why I am taking an impulse? Because the best way of representing a disturbance is nothing but the impulse. The best way of representing a disturbance is nothing but the impulse. And I am applying a disturbance, I am getting the response for the disturbance I am applying. And like that, I am applying the disturbance at each and every instant. So if I add all these disturbances, this becomes my input. This becomes my input at different instances. This becomes my input at different instances. And the response that I got, if I add all of them, then this is nothing but the output for all these disturbances that I have given as an input. This is nothing but my output for all the disturbances I have given. And this adding together is what we are calling as the convoluted result y of n. So what you are doing with the impulse and the response, okay, the inputs that you are having and the impulse response that you are having. What is impulse response? For a single disturbance that you are giving, the response that you are seeing here, okay, whatever disturbance you are giving, the response you are seeing here is nothing but impulse response. Now once you know the impulse response and all the inputs that you are providing, the convolution between these two is what is resulting in the output y of n. So please understand this particular thing, that we are not trying to complicate it. We are just trying to understand what is convolution. Because generally students do not understand or know what is convolution. So convolution is simply you are noting down what the disturbance is, the responses for it. So all these disturbances are added together and all the responses are just added together. The response is what we are calling as the output of the system. So what we are doing between the two of the input and the impulse response, the convolution operation. So this convolution operation is what we are calling as the output. Right. So now I think for this input of 2, 1 and the input of and the impulse response of 1 to 1, the response we got is 2, 5, 4, 1. So this result we can get using the concept of convolution formula also. What is the convolution formula? X of n convolved with h of n is equal to summation k is equal to minus infinity infinity x of k h of n minus k. Okay, so now let me consider any instant that we can have. Okay, let me use this particular formula and see whatever result I got in a physical way, is it actually able to getting using this particular formula. Let me select the instant of n equal to 0. So if I select the instant of n equal to 0, y of 0 is going to be summation k is equal to minus infinity to infinity x of k into h of minus k. Correct or not? X of k into h of minus k. I have just taken the value of n is equal to 0. Yes or no? Now what I am going to do, I am going to take the different values of k here. Let us start with k is equal to 0. At k is equal to 0, you are having x of 0 multiplied by h of minus 0. And at k is equal to 1, you are having x of 1, h of minus 1. You have x of 2, h of minus 2. The other side, if I go, it is x of minus 1 if I take the value of k is equal to minus 1. If I take the value of k is equal to minus 1, x of minus 1 into h of 1, x of minus 2 into h of 2, and of course because of the summation we are just adding them together. X of 0 multiplied by h of 0, x of 0 and h of 0, it is 2. X of 1 and h of minus 1, it is 0 here. X of 2 and h of minus 2, because if you see x of 1 is 1 but h of minus 1 is 0. X of 2 is 0, h of minus 2 is 0. So this side is completely 0. This side x of minus 1 is 0, h of 1 is 0, 2. H of 1 is 2. So 0 multiplied by 2 is 0. Again here also it is 0. So totally it is 2. Totally the value is 2. I was trying to tell you that the h of n did not change for us. The students were thinking that the h of n has changed here. The h of n didn't change. What has changed here? The input has changed. Initially I have kept 0, 1, 0. The response I got was 1 to 1. Now I made it 0, 2, 0. It is the input which has changed, which led to the output changing. But still our h of n is the same. Okay? Because h of n is nothing but impulse response that we got for unit impulse. So when I apply 0, 1, 0, that is what we call as a unit impulse. For unit impulse, whatever response that I got is what we call as an impulse response. It is still the same thing, 1 to 1. So when I calculated here, I got the same 2 that I got here. Like that you can consider any instant. Let me take the instant of 2, n equal to 2. Let me take the instant of n equal to 2. So y of 2 will be, according to formula, what should be y of 2? Summation x of k h of 2 minus k, where k changes from minus infinity to infinity. Now let me again take k is equal to 0, k is equal to 0, x of 0, h of 2, k is equal to 1, x of 1, h of 1. K is equal to 2, x of 2, h of 0. K is equal to 3, x of 3, h of minus 1. The other side, k is equal to minus 1, x of minus 1, k is equal to minus 1, h of 3. K is equal to minus 2, x of minus 2, h of 4. Summation, add all of them till infinity. Now let us see the value x of 0. X of 0, x of 0 is 2. What is the value of h of 2? H of 0, h of 1, h of 2. It is 1. X of minus 1 is 0. X of minus 2 is also 0. The other side, x of 1 is 1 multiplied by h of 1 is 2. Next, x of 2 is 0. H of 0 is 1. Here also, x of 3 is 0. H of minus 1 is also 0. Now if you add all of them, this is nothing but 4. What is this 4? Y of 0, y of 1, y of 2. Okay. So whatever concept we are applying logically, this is what we are logically applying. When you know that when you apply some impulse here, 0, 1, 0, the output is 1, 2, 1. Now what I'm doing, I'm multiplying by 2. So even your impulse response is going to be multiplied by 2. So I got this one. Now if I change the instant, of the disturbance here was happening at n equal to 0. Now I'm changing the disturbance to n equal to 1. We call it as del of n minus 1. According to time invariance, if I give del of n minus 1 here, it should be h of n minus 1. And that is exactly what I got. When I add these two, I got the input x of n. This is what I am applying, right? It doesn't mean that this is not an input. This is also an input. But this is what we are dedicatedly calling as impulses. Impulse, delayed impulse. So when you add them together, this is what the overall input that I have applied. This is the overall input that I have applied. So when I calculate the overall output, it should be the addition of the impulse responses. This is what we are calling as y of n. This is what we are calling as y of n. So to get this y of n, what we are basically doing is nothing but we are using these two only. We are using these two only every time. So the operation that we are doing between both of them is what we are calling as convolution. The operation that we are performing between both of them is what we are calling as convolution. So there is a question from Aghil Kavya that, sir, I don't understand that 2 into h of n. H of n remains the same. Yes, of course. H of n remains the same, right? I'll clarify. See, what is h of n? So this is what I told. H of n does not change means this does not change. Whether you are applying 0, 1, 0, whether you are applying 0 to 0, the h of n remains the same. So if it does 0, 1, 0, then we are calling it as a unit impulse. The response that we are getting for a unit impulse is nothing but impulse response. Now if you are applying 2 here, then what you will get? You will get 2 into h of n. If I apply 3 here, I will get 3 into h of n. If I apply 4, it's 4 into h of n. Right? But does h of n change? H of n is not changing. Your input is changing, the response is changing, but h of n remains the same. Because what is h of n? It's an impulse response, the response that you got from the system when you are applying a unit impulse. When you have applied a unit impulse. Right, so now let us go into the steps of convolution.